Well, we march right on into lesson 19 at Math 221 at SUNY Geneseo, and this lesson is all about extrema on an interval. And extrema is just a fancy term. Extrema just means we're looking for maximum or minimum values on an interval. What's the highest a function goes? What's the lowest a function goes on a particular interval? There's not a lot of cranking out to do in this lesson. It is very vocabulary heavy. It's very theorem heavy. So buckle up because we jump on the vocabulary train. Your author Strang starts with a definition. Let f be a function defined over some interval I for interval. Let c be some number in the interval I. We say that f has an absolute maximum on I at c if f of c is greater than or equal to f of x for all x in I. What does that mean? So you've got some function. That function does various things. If this is the highest point, if f of c is greater than or equal to f of x for all of the other x's, then f has an absolute maximum on the interval at c. And similarly for minimum, we can take a look and say this is the minimum because f of this is less than or equal to every other function value on the interval. We say that f of c is the absolute max on this interval. We say that the absolute max occurs at x equals c. The max is the y value. It occurs at an x value. There's this picture in your book on page 367. It's in section 4.3, or at least it is on page 367 in the 2018 version of the OpenStax calculus book. You should take a moment to look at the picture to say, okay, I understand. This is what it means to have a max. This is what it means to have a min. For example, the cosine function has an absolute max of 1, and that absolute max occurs more than once. That's fine. There's also an absolute minimum of -1, and that absolute minimum of -1 occurs in multiple places, and that's fine. You should also be comfortable with the fact that it's fine for a function to have an absolute max, but no min. And it's fine for a function to have an absolute max and an absolute min. And it's okay for a function to have an absolute min and no max. Okay, here's what we do know. If a function is continuous over a closed interval, then there is a point where there's a max and there is a point where there's a min. If the interval is closed and the function is continuous, then the function must top out and must bottom out on that interval. This almost makes sense. We will use this later in the lesson when we do some cranking stuff out. We should also talk about what we mean by a local maximum. So you take this function here. This is a picture in your book. It's currently on page 368. It's in section 4.3. The absolute max is here. So f of 2 is the absolute max. But there's this other point over here. This point is the max, but it's not the max everywhere. It's just the max in this little interval. And if that's the case, we call that a local maximum. There is a local maximum at x equals 0 because f of 0 is the highest y value in a neighborhood, in a small area that includes 0. Similarly, f of 1 is a local minimum value because f of 1 is the lowest point in an interval that contains 1, in some open interval that contains 1. So an absolute max is also a local max because, well, this is the highest point in this interval. And an absolute min is generally a local min because we can take an open interval and say, yes, that's the lowest point. But not all local extrema are absolute extrema. One more bit of definition stuff. We say that C is a critical point of f if the derivative there is 0 or if the derivative there is undefined. Critical points are places where the derivative is 0 or the derivative is undefined, where the tangent line is flat or the tangent line doesn't exist. So that's a critical point. That's a critical point. That's a critical point. There is a connection between critical points and extrema, and that connection is if f has a local extremum and if f has a derivative, then that derivative has to be 0. If there's a max or a min and the derivative exists there, then the derivative is 0 there. And that's a key. There is a proof of that. It is in your text. It is worth reading. It is not always true that because the derivative is 0, there is a max or a min. This is a case where the derivative is 0, but there is no local extremum there. There's a max, flat tan. There's a max, no tan. There's a min, no tan. But it's not even true that here's a place where the derivative doesn't exist, but there's no extremum there either. So if there's a max or a min and there's a derivative, the derivative is 0. So find the absolute extrema for f of x equals 2x squared minus 8x plus 7 on 0, 3. So there's a couple of ways to skin this cat. One would be that we would plug in every value we can imagine between 0 and 3 and see what the highest high and the lowest low are, but that will take us a while, and so let's not do that. Let's do something different. Here's the something different I propose. If there are going to be absolute extrema, they occur at critical points or endpoints. Critical points or endpoints. The endpoints are easy. We can figure out what f of 0 is. We can figure out what f of 3 is. F of 0, that's 7. And f of 3, that's harder. That's 18 minus 24 plus 7. That sounds like 1. That sounds like 1. So the critical points, that's a doozy. Critical points are places where the derivative is 0 or undefined. This is always defined. So f prime of x is 0 when 4x minus 8 is 0. That means that x is 2. So critical points are endpoints. Endpoints we've already covered. Critical point. When x is 2, that's, oh boy, 8 minus, I can do this, 16 plus 7, put me in, coach, -1. If there are going to be absolute maxes and mins for this function on this interval, they will occur at an endpoint or they will occur at a critical point. So these are the only candidates in the world. The highest high is the max, the lowest low is the min, So the absolute max is 7, and the absolute min is -1. Coach, we'd love it if you'd do that one more time. Well, I'd be glad to. Find absolute extrema for g of x equals x squared minus 4 to the fourth, that does say to the fourth, on -1 to 3. So if there are going to be absolute maxes and mins, they occur at critical points or endpoints. So finding g of -1 is important. Finding g of 3 is important. G of -1, that's 1 minus 4, that's -3 to the fourth, that's 81. G of 3, that's 9 minus 4, that's 5 to the fourth, that's really big. Critical points. How do you find g prime? Well, this is something squared. No, that's not true. This is something to the fourth power, so the derivative of something to the fourth power is 4 times that something cubed times the derivative of the inside. And we think about where g prime is 0 or undefined. This is never undefined, so we consider when g prime equals 0. Well, that happens when x is 0 or when x is plus or minus 2. We ignore the minus 2, so we want to know where g is at 0 and where g is at 2. G of 0, that's -4 to the fourth, that's 256. And at 2, that's 0 to the fourth. I can do that. These are the only candidates in the whole wide world. Critical points are endpoints. Those are the only candidates in the whole wide world. So what does that tell us? That tells us that the absolute extrema, the absolute max is the highest high. That's 625. And the absolute min is the lowest low. And there they are for you to consider. Find the absolute extrema, both for g of x equals 1 over x squared plus 1 on the interval from 0 to 2, and for the function h of x equals x cubed minus 3x squared plus 3x minus 2 on the interval from 0 to 3. We should talk about those when we gather. I'll see you then.